Turning forces for A-level physics. The centre of mass of an object is the point where all the mass appears to be. It's where the weight appears to act. Centre of mass helps calculation of the motion of complicated shaped objects. The track of the centre of mass is a simple path with easy maths. The centre of mass of an object is on the axis of symmetry and usually inside the object. There are a few exceptions to this: dull balancing toys and high jumpers doing the Fosbury flop. An object is stable if the line of action of its weight stays inside its footprint on the ground. If the line of action of the weight passes outside the footprint, this turning force makes the object pivot about its outside edge and it topples over. An object turns if a force acting on it does not act through its centre of mass, or if it's constrained by a hinge. Turning force is an old physics idea, so it has many names and units, but the SI unit that you use in A-level physics is the Newton metre. A turning force is calculated using force times distance to the pivot. But which distance? There's an infinite number of distances to pick. The distance used is the shortest possible distance between the line of action of the force and the pivot. This is the distance at right angles to the force. It's called the perpendicular distance. A turning force, or the moment of a force, is defined to be the force times the perpendicular distance to the line of action of the force. If the turning force acting on the wheel is unbalanced, the wheel will spin faster and faster. It will accelerate. This is angular acceleration. But if a bit of brake is applied so that the driving force equals the braking force, the forces balance, the system is in equilibrium, and we can say sum of all the moments is equal to 0, or the sum of all the clockwise moments equals the sum of all the anti-clockwise moments. A special case of turning force is a couple. This is two equal forces acting in opposite directions equidistant from a pivot. Examples of couples are taps, steering wheels and screwdrivers. The net turning force is calculated in the usual way. The anti-clockwise moment here is equal to the force up times the radius plus the force down times the radius. But the modulus, the size of the down force, is the same as the up force, so we can say anti-clockwise moment equals 2 times the up force times r. For a couple, the net turning force equals the size of one force multiplied by the distance between them. At A-level, turning force problems have two complications compared to GCSE. The first complication is that they just give you loads of forces to organise. The second complication is that the distance you're given to the line of action of the force is not the perpendicular distance to the pivot. You're fairly unlikely to have both complications in one question though. Given the mass of the plank and its occupants, what are the support forces in the trestles? You need to know some length measurements as well to work this out, but I'll give you those later to avoid a bit of screen clutter. What we do know is that this system is in equilibrium because it's not accelerating. The first step to solving this is to draw all the forces acting on the system. Label all the forces as you insert them and use symbols for the unknown ones. Subscripts are really helpful here. The next step is to decide where to put the pivot. Cunningly, any force that acts through the pivot has no turning effect because the perpendicular distance is 0, so you can eliminate one unknown force by plonking the pivot on top of it. Systematically draw in all the force to pivot distances. There's usually a bit of arithmetic to sort this out, but it's not tricky. Remember, you own the exam paper. Draw anything you need onto that diagram. Finally, we're ready to set up the equation for this problem. Start at one end of the plank and work along systematically. Every time you reach force, you ask how big, how far is it from the pivot, and is it clockwise or anti-clockwise, and then you add it to the right part of the equation. This equation has only one unknown and it should be straightforward to solve. In an exam, find the other unknown force by the easiest, quickest method, that might be resolving vertically. If you're learning this technique, find F left using moments as practice, then check your answer by resolving the forces vertically. You should find that the force from the right trestle is 837 Newton, the left trestle supports 1013 Newton, and the total force in both the up and the down directions is 1850 Newton. The second turning force complication happens when the distance you're given to the line of action of the force is not the perpendicular distance. Given the size and mass of this sign, find the tension in the support ribbon. This is a three-force problem which can be tackled in several ways, including using moments. You can eliminate the unknown reaction force by putting the pivot where the horizontal rod meets the wall. This is reasonable because if the ribbon is cut, the sign turns about this point. Use the lengths of the sign to find the angle of the support ribbon. Find the perpendicular distance to the line of action of the force using more trigonometry. Start at the left-hand end of the bar and work along, populating the equilibrium equation every time you reach a force. You should find that the tension in the ribbon is 171 Newton.